All right, welcome. Today, we're diving headfirst into the absolutely wild world of high-speed flight. This is a place where the normal rules of physics kind of get thrown out the window. We're going to uncover the secrets of how to fly faster than sound itself.
So let's start with the big question. How do you actually break the sound barrier? It's not as simple as just building a more powerful engine. See, there's a point where just pushing harder on the gas, well, it stops working. The real answer lies in some seriously strange and, pretty counterintuitive physics.
So here's how we're going to tackle this. First, we'll get into what compressible flow even is. Then, we'll look at the energy of speed, and I promise, we'll reveal the big secret to going supersonic. After that, we'll talk about riding shockwaves, and finally, we'll see how all this crazy physics shows up in actual jets and rockets. Okay, let's get right into it. Our first stop is getting our heads around this idea of compressible flow. This is really the point where our everyday gut feelings about how things move, they just start to break down. You see, at low speeds, air pretty much acts like water. It just flows smoothly around stuff. But as you get closer to the speed of sound, you're moving so fast the air molecules literally can't get out of the way in time. They just start to pile up, they get all bunched together, and the air's density, it changes. A lot. The air actually gets compressed or squished. And that, right there, changes everything. So to even talk about these incredible speeds, we need a different kind of measuring stick. That's the Mach number. All it is your speed divided by the speed of sound right where you are. If your Mach number is less than 1, you're subsonic. If it's greater than 1, you, my friend, are supersonic. This is the magic number for everything we're about to talk about.
But speed isn't just some number on a dial. It's a form of energy. And if we really want to understand supersonic flight, we got to follow the energy. So where does all that go actually come from? Okay. To track that energy, we've got to wrap our heads around a concept called stagnation. Now, just imagine for a second, you take a little parcel of moving air and you bring it to a dead stop. Instantly, all of its motion energy, its kinetic energy, it has to go somewhere, right? Well, it gets converted back into the air's internal energy, which changes its temperature and pressure. That total energy state is what we call its stagnation properties.
So let's just break this down to make it super clear. Static properties, that's the air as it is, as it's flowing along. It's the actual temperature, the actual pressure. Stagnation properties, on the other hand, well, that's its total energy potential. Think of it like this. Static temperature is the cool breeze you feel on your face. Stagnation temperature is how scorching hot that air would get if it slammed into a wall and stopped completely. And believe me, this isn't just some abstract idea. Air moving at a pretty brisk 100 meters per second, that's about 220 miles an hour, has what we call a dynamic temperature of 5 Kelvin. That means if you stopped it, its temperature would literally jump by 5 degrees Celsius. Now imagine what happens at supersonic speeds. This effect becomes absolutely massive. And all of this, it points to a really fundamental trade-off. To make a fluid go faster, you have to pay for it. And you pay for it with its own internal energy. You are literally converting the fluid's own heat directly into speed. So this energy trade-off, it's the key that unlocks the whole thing. If speeding up air means you're turning its own heat into motion, then how on earth do you design something to do that efficiently enough to break the sound barrier? Well, that brings us to the supersonic secret. I mean, think about a garden hose, right? We've all done this. You put your thumb over the end, you make the opening smaller, that's a converging nozzle. And what happens? The water shoots out faster. Simple. So why can't we just do that with air? Just keep squeezing it through a smaller and smaller nozzle until it goes supersonic. Here's why. And this is the part that just blows my mind. The moment you cross the speed of sound, the rules of physics flip completely upside down. Below Mach 1, when you're subsonic, you have to decrease the area to speed things up. That's our garden hose. But for supersonic flow, for flow above Mach 1, you have to do the exact opposite. To make the gas go even faster, you have to increase the area. This is the whole secret right here. And this totally bizarre physics leads to this brilliant piece of engineering called the converging-diverging nozzle. It's beautiful. So first, you've got the converging section, which squeezes the gas, speeding it up right to the edge, to exactly Mach 1. That happens at the narrowest point, called the throat. Then, past the throat, the nozzle opens back up. It diverges. And because the flow is now supersonic, this expansion, it forces the gas to accelerate even more, to Mach 2, Mach 3, whatever you've designed it for. Now, once that throat hits Mach 1, a special condition happens. It's called choked flow. Basically, the nozzle is now a fire hose that's turned on full blast. It's passing the absolute maximum amount of air it possibly can. It's like a highway that's completely full. You can't get any more cars onto it no matter how much you want to. The flow rate is maxed out.
Okay, so accelerating is one thing, but the supersonic world is also home to one of the most abrupt, most violent things in all of fluid dynamics. We need to talk about shock waves. A shock wave is just this paper-thin region where the properties of the air, pressure, temperature, density, they change almost instantly. It's the universe's ultimate traffic jam. It's the point where information, which travels at the speed of sound, just can't get ahead of the flow anymore. So the molecules have no warning, and they just pile into each other, creating this wall. Now, the simplest kind is called a normal shock. It stands straight up, totally perpendicular to the flow. When supersonic air hits this invisible wall, it's like slamming on the brakes. It instantly drops back down to subsonic speed. And this whole process is incredibly inefficient. We call it highly irreversible, which is just a fancy way of saying a ton of useful energy gets wasted as heat.
And look at the chaos it causes. The Mach number, of course, plummets from supersonic to subsonic. The velocity slams on the brakes, and in exchange for that, the static pressure and temperature go through the roof. But here's the real smoking gun, the stagnation pressure. Remember, that's our measure of the flow's total useful energy. It decreases. That drop tells you that energy has been lost, it's been wasted, turned into useless heat. Of course, it's not always so dramatic. You also get oblique shocks, which are angled, like the ones you see coming off the wing of a fighter jet. And you also get the opposite, expansion waves, which are these smooth fans that actually accelerate supersonic flow as it turns a corner. It's this wild dance of compression and expansion. So, wow, that was a lot of physics. Compressible flow, nozzles, shocks. But why does it matter? Well, this is where it all comes together in the incredible machines that actually fly faster than sound. We see this stuff everywhere. Rocket engines? They are the ultimate expression of that converging-diverging nozzle we talked about, turning hot gas into pure thrust. Supersonic jets? Their inlets cleverly use shock waves to do the opposite, to slow the air down before it hits the engine. The space shuttle coming back to Earth? Its blunt nose created a massive shockwave out front to handle all that heat. And for the future, for hypersonic flight, managing these shocks is the #1 challenge. So, you see, it all comes down to this. From that weird, counterintuitive shape of a rocket nozzle to the violent, invisible wall of a shockwave, understanding and mastering the bizarre physics of compressible flow is the absolute key to flying fast. But you know what? The story is not over, not by a long shot. That incredibly complex place where a shockwave actually smashes into the thin layer of air clinging to a wing, that's still one of the biggest hurdles in aerospace engineering. So as we try to fly even faster, pushing into the hypersonic realm, what other secrets, what new physics are still out there waiting for us to find?